Hi there. In the previous video you saw how a hypothesis test was performed on the success probability of a new type of surgery. We had the two hypotheses, the test statistic t, the distribution of t under the assumption of the null hypothesis, and the p-value, which led to the conclusion. This p-value was the probability, assuming the null hypothesis, that the test statistic has the observed value or a value that gives even stronger evidence for the alternative hypothesis. So this means that if the null hypothesis is true, we have about a 1 in 10 million probability of making a type 1 error. Now, sometimes you want to have an upper bound for this type 1 error probability. Let's consider this in the following example. On a motorway, the speed limit is set at 100 kilometers per hour. Let's call the actual velocity of a certain car mu. The police want to check whether people keep to this limit. If according to them, people do not keep to this limit, they will issue a fine. Well, this boils down to a hypothesis test. The null hypothesis is that someone is driving at the allowed velocity, i.e. mu equals 100. The alternative hypothesis, for which the police seek evidence, is that the actual velocity exceeds this value. In order to make the decision, the police measure the velocity of the passing cars. As in all measurements, this is not exact. Rather, the measured velocity x of a given car is equal to its actual velocity mu plus a measurement error y, which has a normal distribution with expectation 0 and standard deviation 0.5. This standard deviation has to do with the calibration of the measuring device, so it does make sense that this is a known value. It can be communicated by the manufacturer of the device. Notice that mu is just the actual velocity of this one car. There is no randomness there. We find that x has a normal distribution with parameters mu and 0.5 squared. The question now is, for which measured velocity should the police issue a fine? Intuitively you might say, well, they should fine if the measured velocity exceeds 100. However, a person driving at exactly 100 km per hour then has a 1 in 2 probability of getting fined. That seems very harsh. Rather, the government will at this point step in and require that people driving at exactly the allowed velocity should have at most a certain probability of getting fined. Let's say that they want this probability to be just 1%. So, out of 100 people who drive at exactly the allowed velocity, on average at most 1 should unjustly get a fine. This upper bound is called the significance level. It leads to a very straightforward decision rule. If the p-value is smaller than the significance level, then we reject the null hypothesis. Otherwise, we don't. In this way, the probability of a type 1 error, getting a fine, for someone who drives at exactly the allowed velocity will be 1%, exactly as the government requires. Here you see the probability density function of the measured velocity for someone who drives at exactly 100 km per hour. Let's call the threshold velocity c. If the measured velocity is less than c, the police will not issue a fine. If it is at least c, then they will issue a fine. This means that we want the probability that x is at least c to be 0.01. Well, we know how to compute probabilities involving the normal distribution, and we find c equals 101.16. Notice the R code. We used the qnorm command with parameters 0.99, since we want 99% of the area to be to the left of c, parameter 100, the mean, and parameter 0.5, the standard deviation. Using this command, we actually did not need a transformation to a standard normal. We call this c the critical value. Do pause the video if you want to check this computation for yourself. It means that the significance level 0.01 can easily be interpreted graphically. It is the area below the graph of the density function according to the null hypothesis, above the region where the null hypothesis is rejected. It is indicated in orange in our sketch. Any observation that is less than C will lead to a p-value that is greater than 0.01, so it will lead to not rejecting the null hypothesis. Any observation that is greater than C will lead to a p-value that is less than 0.01, so it will lead to rejecting the null hypothesis. The set of all these observations for which we do reject the null hypothesis is called the critical region. Now, let's take a step back. We have been considering type 1 errors so far. Then it will not come as a surprise that there also exists a type 2 error. And this makes sense. There are actually 4 possible situations. The person could be driving at 100 km per hour, so they are not speeding. Well, they could then not be fined, which would be the correct decision, or they could unjustly be fined, which was our type 1 error. On the other hand, the person could be exceeding the 100 km per hour limit. In this case, they could be fined, which would be the correct decision, or they could unjustly not be issued a fine. Well, this is called a type 2 error. By the way, you might say that people can also drive slower than the speed limit. They will have an even lower probability of a type 1 error. This is sometimes also incorporated in the null hypothesis, which will then take the form mu is less than or equal to 100. We call this a composite null hypothesis, but since it complicates things quite a bit, we will not work with this any further. We already know that the type 1 error probability is 0.01. This was our fixed significance level alpha. But what about the type 2 error probability? Well, this actually depends on the way that the alternative hypothesis is true. Indeed, someone who is driving at 101 will have a far higher probability of not being fined than someone who is driving at 110. Okay, let's consider someone driving at 102 km per hour. This is their actual velocity mu. So the measured velocity has a normal distribution with still the same standard deviation 0.5, but now with expectation 102. We know that the police issue a fine if the measured velocity is at least c, which was 101.16. Probability of a type 2 error is the probability that they do not get a fine, which means that the measured velocity does not exceed c. This probability equals 0.047. As you can see, this type 2 error probability corresponds to the area in green, the one below the density function for this actual velocity of 102, to the left of the critical value c. This probability is denoted by beta. Its complement, 1 minus beta, is called the power of the test at mu equals 102. It is the probability of correctly rejecting the null hypothesis in the case that the alternative hypothesis is true in the sense that mu equals 102. The power function of a test can be used to compare hypothesis tests based on different test statistics. Actually, in much the same way as the MSE could be used to compare estimators. Alright, let's play with these graphs for a bit. Without doing any computations, what will happen to the type 2 error probability if someone drives at 102.5 km per hour? Well, this probability will decrease. The first curve and the value of c remain the same, but the second one shifts to the right, so that the area to the left of c decreases. Feel free to check the math. You should find beta equals 0.004 now. Okay, back to the person driving at 102. What if the government says it's not too bad if more people unjustly get fined, and they fix alpha at 0.05 rather than 0.01? What will change? Well, the type 1 error probability, which is the area in orange, goes up from 0.01 to 0.05. As a consequence, the critical value moves to the left, and the type 2 error probability, the area in green, goes down. Well, there is indeed a trade-off between the probabilities of type 1 and type 2 errors. The lower you want one of them to be, the higher the other one will get. Well, to conclude this story, could you think of a way to get a lower beta for someone driving at 102, while keeping alpha at the value of 0.01 that we started out with? Well, if the police invest in better measurement devices with a lower standard deviation, say 0.4 rather than 0.5, then the density functions will be more concentrated around the expectation. There will be less overlap between the curves. This will allow us to have a smaller beta for the same alpha. Notice that also the critical value decreases as a consequence of the new standard deviation. Okay, in the next video we will cover a particular test, the t-test. See you then!